This video is going to walk through some examples that have you solve functions that have trig functions in them, and it will indicate where you are to solve those, like the range of values or the domain values that you're actually going to look at unit circle graph wise. And for each of these examples, I've included a graph of what it looks like on the graphing calculator. So you can see either where the graphs intersect or you can see where they have zeros, just to sort of give you an idea of how many answers you should end up having. But otherwise, it'll use trig identities and relationships and formulas and substitute and try to clean up and get the angle by itself so we can solve for them. So for this first example, we have 3 cosine squared of theta plus sine squared of theta. I have graphed the left equation in y1, the right equation in y2 on my graphing calculator. And you can see that we should end up with 1, 2, 3, 4 solutions where those two graphs are equal to each other. Now, to solve for it, your calculator will give you decimal answers if it's in radian mode, which it currently is. So my window is looking from 0 to 2 pi. If you set your window from 0 to 360 in graph, it will give you and show you intersection answers in degrees, and then you would have to convert those to radians. But for now, we're just going to work in radians. So I need to simplify my equation so that I can solve for theta and find answers that satisfy this equation. So I have a cosine squared and I have a sine squared. Now I could rewrite one in terms of the other. I could write cosine squared as sine squared minus 1. Or I could write sine squared as cosine squared minus 1. You could do that, and then you'd have to combine like terms and factor. Those are certainly options you could work through, but I'm going to use the fact that if I divide cosine squared over, I'm not getting rid of it. I'm just going to combine the fact that sine over cosine is the same thing as tangent. So again, the division you want to stay away from if it deletes and completely eliminates a function. We're not eliminating a function by dividing cosine here. We're simply combining cosine under sine to give us tangent. So now I can solve tangent squared equals to 3. If I plus and minus square root both sides, that would give me that tangent of theta is plus and minus square root of 3. So that gives me two different solutions to work from. It gives me that the tangent of theta is positive square root of 3, or that the tangent of theta is negative square root of 3. Now, from unit circle, you have the points that are either 1/2 square root of 3 over 2, or you have square root of 3 over 2 and 1/2. Those are the points that you'll be choosing from. And the tangent ratio puts y over x. So we'll have to choose the ordered pair for which we put y over x gives us a whole square root of 3. So we'll be using the point 1/2 square root of 3 over 2, which happens at, your pi over 3, your 2 pi over 3. It happens at your pi over 3s. But we need to choose, to begin with, we need our tangent ratio to be positive. So that happens in quadrants 1 and 3, because in quadrant 3 they're both negative. So in quadrant 1, where I can get a tangent ratio of square root of 3 is at pi over 3, because again I'm putting y over x. That would put square root of 3 over 2 over 1/2, which would be square root of 3 over 2 times 2 over 1, and I would get the square root of 3 for my tangent ratio. So I have the square root of pi over 3, and then down in quadrant 3, if I pull 4 pi over 3, that would be negative root 3 over 2 over negative 1/2, and I would get the positive square root of 3 again. So there's two solutions. And then using our negative aspect, the tangent ratio is going to be negative in quadrants 2 and 4. Because in quadrant 2 and 4, you have the x and the y coordinate have opposite signs. One's positive and one's negatives. And again, we need to pull root 3 over 2 over 1/2 in that order for y and x. So in quadrant 2, my angle will be 2 pi over 3. And in quadrant 4, my angle would be 5 pi over 3. So there are my 4 distinct solutions for 3 cosine squared equals sine squared. And you could, again, if you got those 4 intersection points, right, doing the intersection by graphing y1 and y2, then going second trace, which puts you in a calc menu, and then choosing option 5 to intersect. But you'll have to get, right at each intersection point to give first line, second line, and then to guess, and then you'll have to do that for all 4. But that would only give you the decimal representations, and you need to be able to give the exact answer values, especially if they come off of the unit circle. All right. Next question. Sine of 2 theta minus cosine of theta equals 0. And we're looking from 0 to 2 pi, and I want to know where it equals 0. So to do that, I graphed it, and because we set it equal to 0, you would be looking for the zeros of the function, which is where the x-intercepts are. So there's 1, 2, 3, 4 here for this problem again, from 0 to 2 pi. So I need to look at, again, you can calculate the zeros by going to the left and to the right of the x-intercept and get those decimal answers, but we need to be able to give exact. So I have a double angle on sine, and then I have a regular cosine. So if I go through and replace the sine of 2 theta has a double angle, there's only one for the sine of 2 theta, and I could replace it with the double angle formula that says sine of 2 theta is 2 sine theta cosine theta, and then I have minus cosine theta equals 0. I can note that I have 2 separate terms for which they both have a cosine in them. Cosine here, cosine here. So I could factor out a cosine. It's a single cosine. And I'm left with 2 sine theta minus 1. And then now I have 2 separate quantities that are being multiplied. Again, nothing needs to be simplified. It's just one single cosine and then a single sine that I could solve. So when I set each of those equal to 0, I have cosine of theta equals 0, or 2 sine theta minus 1 equals 0. And now I'll solve each one for theta. Cosine theta is already solved, so where is the cosine of an angle 0? Where is the x-coordinate on the unit circle 0? And that happens at 2 places. It happens up at pi over 2, 90 degrees, and it also happens down at 3 pi over 2, or the 270 degrees. But that's exactly where the cosine of theta is 0. Okay, for the other solutions, if I add 1 and divide by 2, I'm looking to find theta where the sine of theta is 1/2. And remember, sine is the y-coordinate, so that's exact. We can pull those exact values from our unit circle. Our y-coordinate is 1/2 and positive in quadrants 1 and 2. And the sine value in particular being 1/2 happens at pi over 6, which is at your 30-degree mark, or it happens at 5 pi over 6, which is over at your 150-degree mark. So we have 4 different solutions that will make our sine of 2 theta minus cosine of theta equals 0 from 0 to 2 pi. All right. So next question has some cosines in it. I have graphed them separately. The 5 cosine of x is the lighter, thinner graph, and the 1 over cosine of x is the thicker graph. So because I graphed them separately in y1 and y2, I'm looking where they intersect. And these actually have 1, 2, 3, 4 intersection points. So there will be 4 values that make this answer true, equal, solution. So for this one, 1 over cosine is secant, but it doesn't really benefit you to write that as secant. You can't substitute. It's not a secant squared. There's no identity for it. So what you could do for this problem is, since there are 2 cosines, and one's in the denominator, if I multiply both sides by cosine, it would get my 1 cosine out of the denominator. It doesn't get rid of a solution. It's just cosine of x can't be 0, or it would be undefined. So we multiply both sides by cosine of x. On the left side, I have 5 cosine squared equals 1. Okay, I have a function that's squared, and I'm trying to solve for x in that function, and we can use our square root property that we've done before, when we had x's. The square root property that said You know, if you have x squared equals a number, you get that x by itself, then you can plus and minus square root both sides to find your solution. So your x would have been plus and the minus the square root of whatever that number was. It's called the square root property. Use it to solve quadratics that just have an x squared in a number. That's a really easy property to use to solve those. So for our cosine squared function, I can divide both sides by 5, and I'll get cosine squared of x equals 1/5. And again, remember, cosine squared of x is just like the cosine of x squared. So I am allowed to square root that. And when I square root both sides, I get that cosine of x is plus or minus the square root of 1/5. The square root of 1 is 1. And so I could rewrite that as 1 over the square root of 5. Or if you'd like to think of it rationalized, square root of 5 over 5. Those are all numerically the same thing. Calculator will handle all of them. Okay. So we're trying to find where our cosine is this irrational number. And it's not exact. It's not like a root 3 that we can pull from the unit circle or a square root of 2 that we can pull from the unit circle. So it's not exact for our unit circle information. But what it does present is two separate parts. I have that the cosine of x is a positive 1 over square root of 5, or I have that the cosine of x is a negative 1 over the square root of 5. And so each of those are going to give me two solutions, because there's two places on the graph where x is, or the cosine is positive. There's two places that match each other where the cosine is negative. Let's see, 1 over square root of 5. Again, this is like approximately 0.4472, or approximately negative 0.4472. So that's our cosine values, and we're trying to find x, the angle that makes that true. So anytime that we needed to find x, and we weren't pulling from the unit circle, we use the inverse functions. So we'll do cosine inverse of 1 over square root of 5, and I'm in radian mode, because I need to go from 0 to 2 pi. My answers need to be in radian, so I'll stay in radian mode. So if I do the cosine inverse of 1 over root 5, I get 1.107 and some change. I wouldn't round too soon, but that's going to be one of the radian answers. And just to give you, mindset, this is also like 63.4 degrees. So picture-wise, one angle is here at 1.107 radians. So that's what one angle is in quadrant 1. That's where the cosine was 1 over square root of 5, or 0.44. So because I'm in quadrant 1, I do also have a matching angle down in quadrant 4 that has the same cosine value as the 1.107 angle does. So this angle is 1.107 radians. And I have a comparable angle from 0, again, we're going 0 to 2 pi, that from 0 all the way around to that radian measure has the exact same cosine value. Now, to come up with what that angle is, that larger angle that wraps over 3 quadrants, the easiest thing that you could do is notice this 1.107 that you went up off of the x-axis. We'll go the same 1.107 down from 2 pi and still be in the same location. So to come up with that fourth quadrant answer, I'll do 2 pi minus the 1.107 answer, and I'll get a radian value of 5.176. So that's the other angle that has a cosine value of 1 over square root of 5. So I have two answers from that. I have 1.107 and 5.176. Okay. For the other two solutions, or for the other cosine answer, so now we're looking where cosine is negative 1 over square root of 5. So you can do cosine inverse of negative 1 over square root of 5 in radian mode, because it'll give you a different value. It gives me that x is 2.034, which, again, to put you in the mindset of where that lives, it's 116 degrees, 116.56. So picture-wise, it's over here, somewhere like that, maybe 90 degrees up top. So there is my large 2.034 radian angle that lives in quadrant 2 that has a cosine of negative 1 over square root of 5. But it will also have a match with the same negative cosine value that lives down here in quadrant 3. But the angle that we need an answer for is the larger, again, from 0 to 2 pi, we start at 0 and we wrap around over 2 quadrants, and that's the radian answer that I need. And so to get that, it's the mirror image of the one up top. So you can't, you don't know what the reference angle is here to subtract it or add it to pi. So we won't attack it that way. But what I can note is that if I go, I'm going to use a different color that shows up a little better, from 0 and wrap the negative direction, it would have the same it's the same 2.034 radians away from 0. It's in a negative sense. So if I want to get that angle, I could do 2 pi minus 2.034 radians, and that would put me in the same spot, which is 4.249. So the other two answers here are 2.034 and 4.249. So you do get 4 solutions. They would be the same 4 decimal solutions that you could have gotten from the intersections on the graph, and in increasing order, the 1.1, the 2.0, 4.2, 5.1. But those are the 4 radian solutions based on solving for the angle that gives those 2 cosine values. And there's 4 of them. All right. So here's one that has us look at sine squared minus cosine squared equals sine of theta. So the fact that you have, we don't really have an identity for sine squared minus cosine squared. You have the opposite quantity in a double angle formula, but that won't really help you because you still have a sine. And we don't really have a sine squared identity unless it's written in terms of cosine, and the cosine squared identity is written in terms of sine. So what we can do here, because there's a sine squared and a sine, you want to try to rewrite the cosine squared into something that has sine values. So we can use the fact that sine squared plus cosine squared equals 1 and turn that into cosine squared equals 1 minus sine squared, and we can substitute that quantity, which has a sine squared in it, which we already have one of. So we'll have sine squared of theta minus the substituted quantity of 1 minus the sine squared of theta. I'm going to keep that in parentheses because you have to understand you're subtracting that quantity, so we're subtracting that substituted quantity, and that equals sine of theta. I'll distribute through and have sine squared theta minus 1 plus sine squared theta. Be extremely careful with signs. And I'm going to go ahead and minus that sine theta over to the left so I can set it equal to 0. And I can see from my graph that the intersection is 1, 2, 3 answers. And so now I have 2 sine squared terms, which if I combine those are 2 sine squared theta. And then I'm going to rearrange the terms so the sine function is in descending order for its exponents. So I have a squared, a single function, and a subtraction of 1. And now you have a trinomial for which we can attempt to factor. Trinomial, not trinomial. So now we can try to factor. Okay? And if you want to abbreviate the sine squared with s squared so it helps you understand or visualize the factoring better, please feel free. So 2 sine squared is 2 sine times sine. The only way I can get that 1 is 1 times 1. And it needs to be a negative 1, but it also needs to be a negative s in the middle when I do my outer and my inner distribution. So I'll need a 2s with a plus 1 and the s with the minus 1 so that I get negative 2s on the outside plus 1s on the inside, and I have my negative s that I need. Right, so again, we used s's, but it's the same as, 2 sine of theta plus 1 times sine of theta minus 1. And now I have two factored quantities for which there's a single theta. I can set each of those quantities equal to 0. So I have 2 sine theta plus 1 equals 0, or I have sine theta minus 1 equals 0. Solving each of those for theta, I get 2 sine theta equals negative 1. So sine theta is negative 1/2. Or I get that sine of theta is positive 1. So for sine of theta equals 1, remember that's the y-coordinate. And the y-coordinate is only 1 up at pi over 2. Right? So we do that. We have one of our answers up at 90 degrees. And the other one is, where is the y-coordinate negative 1/2? So the y-coordinate's negative down in quadrants 3 and 4. And if you look at your unit circle, you'll see that your y-coordinate is negative 1/2 at 7 pi over 6. And your y-coordinate is also negative 1/2 at 11 pi over 6. So you have three solutions. You're welcome to, again, graph those two equations separately and find their intersections, but it will only give you the decimal representation for those radian values. And you need to be able to answer with exact. All right. Next example is limited to the first quadrant, so it's only from 0 to pi over 2. So when I did the graph, I only did the graph from 0 to pi over 2 in radian mode. So you can see there's only going to be one answer. So it's a tangent function, and we just need to get the tangent function by itself using some algebra. So I'll subtract the 1 and have 2 root 3 tangent of x equals 2. I'll divide both sides by the 2 root 3. So that I can get tangent of x by itself. My 2's cancel, and I'm left with 1 over the square root of 3. Now note that that's also the same as square root of 3 over 3. In case you see it written that way, it's just rationalized, where it pulled the root out of the denominator. So you're not dividing by an irrational number, which would not be possible. So either way, we're looking for a tangent ratio, tangent of the angle, to be 1 over square root of 3, or square root of 3 over 3. So that brings us to, we're only in the first quadrant. So we had 2 points, right? 1/2 root 3 over 2, or root 3 over 2 and 1/2. One's for the pi over 3 at 60 degrees, and one's for the pi over 6 at 30 degrees. So I need the tangent ratio to pull the y over the x coordinate so that it gives me 1 over the square root of 3. So if I do root 3 over 2 over 1/2, those will end up canceling to just square root of 3. If I do 1/2 over square root of 3 over 2, and where it'll multiply 2 over square root of 3, that would give me the right corresponding ratio that I need for tangent, and that is where the y value is 1/2 and the x value is root 3 over 2. So that would be the angle of pi over 6, which is also 30 degrees. Okay, so at pi over 6, I would get the tangent value of that angle to be 1 over the square root of 3. But again, we're only in the first quadrant, and we're not really concerned about where the other ones live. And there we go. Pi over 6. All right, this next one, crazy graph. So I graphed it in two different things, and I want you to notice this. It's a secant squared, which is a crazy graph anyway. And then we added 6 tangent of theta, and it equals 4 tangent of theta. So if I graph them separately and see where they intersect from 0 to 2 pi, I had to play with the window some, but here's the picture from the graphing calculator. The light graph is the left half, the dark graph is the right half, and you can sort of see that they touch each other in 2 places. And then here's the one from Desmos in color, so you can sort of see a little bit more. They just sort of touch at those 2 places. And maybe you can estimate that those would be, in between pi over 2 and pi, and 3 pi over 2 and 2 pi. But we need to be able to find exact. But they only have 2 places where they potentially touch. So now if we look at solving for theta, I have a secant squared, and then I have 2 regular tangent functions. And there is an identity for secant squared that says secant squared is the same thing as 1 plus tangent squared. And if I replace that for secant squared, I'll have tangent squared term, I'll have regular tangent terms, I will have potential for factoring. So if I do that, I'm going to go ahead and move this 4 tangent over to join the 6 tangent and leaves me with positive 2 tangent theta. And now I have 3 terms, a number, a squared term, and a non-squared term where the coefficient, the exponent is just 0. So I do have a trinomial, 3 terms, and I am going to try to factor it. I'm going to rearrange the order of these terms as the squared first, plus the 2 tangent theta plus 1, just so for viewing purposes it's easier to look at factoring. And again, if you need to think of that as like tangent squared plus 2 tangent plus 1 with t's, because your brain factors that easier, feel free. So that would be a tangent times a tangent, or t times a t. 1 and 1 would give you 1, and everything is positive, so both of these would be plus. So you have a repeated quantity of tangent theta plus 1 squared equals 0. So you're only finding really one quantity. You're only setting tangent of theta plus 1 equal to 0 one time because it's a repeated quantity. So if we do that, that's where tangent of theta equals -1. And we're going from 0 to 2 pi. And tangent ratio is y over x. And the only way I can get a ratio of 1 is if I have the same number over itself. And the way I get a -1 is if I have a negative number over the positive or a positive over the negative. But it has to be the same number in order to give me the ratio of 1. So those happen at your 45-degree angles and all of the ones that are comparable to it. So if I want the tangent ratio to be negative, then I'm looking at either quadrants 2 or 4. And those, the 45-degree angles that live in those 2 quadrants are 3 pi over 4 and 7 pi over 4. Those angles in radians, which is what, 135 degrees and 315 degrees, those 2 angles have a tangent value of -1, because if I put their y over their x coordinates, the ratio gives me -1. So there's your 2 answers for that problem. All right. Next question has you look for the cosine of an angle being 0.6, which is like 3/5, but we're going from 0 to 4 pi. So I adjusted my window when I graphed it from 0 to 4 pi, and you'll see that it actually has 4 solutions. 2 pi is the regular period for a cosine graph, so you kind of do have, it repeats twice. See, here's one period where the cosine value was 0.6, and then the next revolution, the cosine value is 0.6 again, so it's very repetitive. So we're actually going to go 2 revolutions around the circle, the unit circle, if you want to think of it that way, as far as location and where they live. So for here, I don't have anything to solve or simplify. I have something to solve. I just don't have something to simplify. The cosine value is 0.6. I'm in radian mode, so if I do cosine inverse of 0.6, I get 0.927295, keeps going on and on and on. Okay, so picture-wise, that is, just again to put you in mindset, that's the same thing as like 53 degrees. So where that would live would be sort of here. There would be a theta of 0.927 radians. And so if I want to know where else the cosine happens to be the positive 0.6, that's an x-coordinate, and the x-coordinate will have the same positive 0.6 down here in quadrant 4. So I'll have the same comparable angle down here in quadrant 4 that will just live in a mirrored location across the x-axis. So it will actually be, again, we're going from 0 to 2 pi, it will have that same reference angle of 0.927 down away from 2 pi. So to get that, we'll just do 2 pi minus 0.927, all those decimals. It's better to keep them all 7295 when you're finding other answers. So this gives me 5.362455807, but rounded 5.362. So there's 2 angles. And again, that just went from 0 to 2 pi. So from 0 to 2 pi, I have those two angles. And if I keep going to 4 pi, all that's going to do is simply wrap around a second time, and it'll hit those spots again a second time, but I have to give them a new number. So if the original angle was 0.927, I can just take 0.927 and add 2 pi, and that wrapped it around the circle again in the counterclockwise positive direction. So if I do 927 plus 2 pi, I get 7.210. And again, the same thing. I had the same angle hit down here in this fourth quadrant again. So I'll just take the 5.362 and I'll add 2 pi again. And that gives me 11.645. So your 4 angle answers were the 0.927, the 5.362, the 7.210, and the 11.645. But all we did was add 2 pi because we just kept going around from 0 to 4 pi. So we just keep adding 2 pi in the positive direction to get those other two solutions. You know, on a related note, had it went like negative 2 pi to 2 pi, you would have first found the solutions from 0 to 2 pi, you know, this direction, and then you could have found the same solutions that went from negative 2 pi to 0 by starting here at 0 and wrapping around in the negative direction. And they would have lived in the same place. You just have to think of it in a negative answer. So just to mention the relatability there. All right, last example has us do tangent of 2 theta plus the tangent of theta from 0 to 2 pi. This has involvement of nothing but tangent. It's a tangent of 2 theta. It's not a tangent squared, so I can't factor it right now. The only thing that I have for any substitution would be, you know, it doesn't become tangent of 3 theta. That's something that you would make up and it wouldn't be true. Tangent of 2 theta is a double angle formula, and I actually have a double angle formula for tangent. That substitutes to be 2 tangent theta over 1 minus tangent squared of theta plus tangent of theta equals 0. All right, now we have a fraction plus a single item. You could try to give it common denominators, but it's still not going to clean up very nicely. But what we can do, because we're involving nothing but these tangents, is I'm going to subtract this tangent over. We're not verifying, so I can move stuff around and have it equal negative tangent of theta. And then I can multiply both sides by that denominator, the 1 minus tangent squared times 1 minus tangent squared. And that would leave me with 2 tangent of theta on the left. And if I distribute, I've had negative tangent theta plus tangent cubed of theta. It's okay, it's like an x cubed. Don't worry, because it's something you haven't seen before. But I have terms that have tangent in them, and I'm going to try to put them on the same side now. I've got rid of my fractions. So if I combine, I'm actually just going to subtract the 2 tangent theta over, because I can. It doesn't really matter which side you make 0. So I have 0 equals negative 3 tangent of theta plus tangent cubed of theta. I might rearrange that and put my tangent cubed first, just because I process better when the degrees descend. So I have tangent cubed theta minus 3 tangent of theta. They both have at least a tangent in common, so if I factor that one out, I have tan squared minus 3, and now I can set each of those equal to 0. I can set tangent of theta equal to 0, and I can set tangent squared of theta minus 3 equal to 0. Tangent of theta is 0 whenever y over x gives you 0, and that would really only happen at those top left, bottom right points where the values are 0 and 1. And the only way you're going to get 0 is if you do 0 over 1 or 0 over negative 1. If you divide by 0, your tangent would be undefined. So the only places where your tangent are 0, again, we're going from 0 to 2 pi. If you notice the graph, This sucker has 1, 2, 3, 4, 5, 6, 7 zeros, 7 x-intercepts from 0 to 2 pi. So we should get 7 distinct solutions here. No, the graph, it's just the way the graph looks for this tangent combination function. So the tangent of theta is 0, where you have the x-coordinate point 1, 0 or negative 1, 0, because that would put y over x and give you the number 0. So those happen at 0, they happen at pi, and they also happen again around at 2 pi. We included 2 pi in our interval, so if 2 pi is a potential solution, it needs to be there. There will be some that go from like 0 to 2 pi and they don't include 2 pi. We don't have that here, but there are some that show up like that, so just be really mindful of the values of numbers it tells you to look between. So there's 3 of them. So then for the other solution set, we have tangent squared of theta equals 3. Anytime we have a squared function equal in a number, we can plus and minus square root. So tangent of theta is plus or minus the square root of 3. So again, that's 2 different outcomes. Either the tangent is positive square root of 3 or the tangent is negative square root of 3. And the square root of 3 is a number that appears on our unit circle. And the only way we're going to get that square root of 3 is if we put square root of 3 over 2 over 1/2. So where our x values are 1/2 and our y values are square root of 3 over 2. So that happens at all your pi over 3 angles. And we need where it's positive root 3. So that's going to come from quadrants 1 and 4. And we'll get at pi over 3 and at 4 pi over 3, the tangent value would be square root of 3, positive. And then for the tangent value to be negative square root of 3, so this was what, quadrant 1 and 3, and the tangent being negative will come from quadrant 2 and 4. And so that is where you have the 2 pi over 3 and 5 pi over 3. Those angles, if you do their y over the x coordinate, would give you a tangent value of negative square root of 3. So there are 1, 2, 3, 4, 5, 6, 7 distinct solutions from 0 to 2 pi, matches what we found on the graph for 7 distinct x-intercepts, and there you have the solution to tan 2 theta plus tangent theta equals 0.